Today's lesson is section 2.5, limits involving infinity. Here we're talking about when we have different parts of our function going to infinity, what kind of happens. So this first one, for letter A, we have the limit of 1 over x as x goes to 0. So you can notice that both sides of that function, one is heading on the right side of 0 is heading to positive infinity, the left side is heading to negative infinity. So we would say does not exist because they're not going to the same thing. For letter B, though, the limit of ln of x is heading towards negative infinity as we're approaching 0 from the right side of the function. So then here we can say that it's just negative infinity. For letter C, for tangent, here we have the same problem as we do for A. As we're approaching the value of pi over 2 from both sides, they're not going to the same thing. So we would say that they are undefined. So the limit, infinite limits, kind of work the same way as if we would have some discontinuity there. And so if they're approaching the same thing, then we get to say that they're approaching that value. So most of the time these happen when we're talking about or looking at a vertical asymptote on the graph. And so if I want, or if I know that a function of f of x is approaching a value of a, for it to be going to infinity, it needs to be going to infinity from the right, and it needs to be going to infinity from the left. Same thing if we were going to negative infinity as we're approaching the value of a. Both sides of our value of a need to be going to negative infinity for that to be true. Now, like we said, if one of those things is off, then it'll be undefined for those points. So now here, if we say that as a goes to infinity, or if we're going from negative infinity to a, like coming from those sides, we can also look at what our values are approaching using an horizontal asymptote. So rational functions are one of the key ones here, where we have a line that our function is approaching as we head to infinity or negative infinity. So usually you're not going to have two sides that you're going to be looking for, but you're looking for a value that they are approaching eventually. Now, they're never going to actually touch it, but we are heading towards that value. And every step, however big it's going to be approaching that value eventually. So here are some examples of those. So if I'm looking at the limit of e to the x as we approach negative infinity, here it looks like we're going to 0 because the value of that exponential function is getting smaller and smaller and heading towards that horizontal asymptote of 0. Same thing with when the limit of negative e to the x is approaching negative infinity. But like trig functions like sine and cosine, you're never approaching anything. You're always oscillating in between 1 and negative 1, so it's undefined. One of our limit laws that we have at our disposal is when n is a positive integer, one of the two things is true, that if I have a limit of 1 over x to the n, or that I'm going to infinity or negative infinity, we actually approach 0 no matter what because of that horizontal asymptote there. And so that'll be a key player in us trying to figure out what our limits are down the road. Now, one thing we want to kind of tie into is something that we did in pre-calculus. And so when we were graphing rational functions, we always talked about where our horizontal asymptotes are going to be. And so one of the things we did was look at the exponents. And so when they were equal, we took the division of the leading coefficient of the numerator divided by the leading coefficient of the denominator to see what that is. And so like in example A, I get 4/3. So in letter B, the exponent and the numerator is less than the exponent and the denominator or the degree. That means that our horizontal asymptote was always going to be y equals 0 no matter what. And then when the leading or the degree of the numerator was bigger than the denominator's degree, then that meant that we didn't have a horizontal asymptote at all. Now we have the tool to be able to show you why that's the case. And looking at the limit, we can actually prove this. Now, one of the tools that I'm using is that limit law that I kind of talked about. If we can make it so our function has some values of 1 over x to some power, we can use that as a tool. Because we're heading towards infinity, we know that that is 0. And so what we're doing with these limits is we're multiplying the top and bottom, so keeping it equivalent, by 1 over the highest power of both the top and the bottom combined, so overall. So looking at both of these, they both have the same exponent, so we would say it's x squared, and so that's how I was multiplying both the top and the bottom by 1 over x squared. And that allows us to simplify, and then notice that for 5x, 5 over x, 1 over x squared, and 7 over x squared, we got to put in zeros. That gives us the 4/3 that we got in the previous example of A. Here, letter B, same thing. Now notice the numerator has a degree of 1, but I'm still going to go with the highest degree overall, both top and bottom. So that's why I'm multiplying by 1 over x squared to both the top and bottom. Here, 3 over x squared and 6 over x get me 0. So allows me to simplify, and that gets me the same horizontal asymptote as I do previously for letter B in the other example. Now letter C, I'm doing the same thing, multiplying both top and bottom by 1 over x squared, and simplifying as best as I can. And also notice not everything simplifies because not everything has an x, but where I notice that there's a 1 over something, so I have 3 terms there, I get to plug in 0. Now here I get 1 over 0, which means it's undefined, which shows that I didn't have a horizontal asymptote for letter C from the previous example. So those are the reasons where or why we get those specific things that we came up with in pre-calc because of limit laws. Now example 3 here, there's a little different things going on. We can't really use the same tactics as we did before, but we can use some other limit laws that we have at our disposal to kind of break this apart. So here, because they're x squared minus x, I can separate them, subtract. Because it's x squared and x, it's really just plugging in the infinity, and infinity minus infinity is not really defined because we don't really know what infinity is. We can't subtract them, so we can't really say it's 0, even though it would be really easy, like if it was 3 minus 3. But we can do something else where we can factor out the x, and because if I'm going to infinity, both are arbitrarily going to go to infinity. It's infinity, and then it's infinity minus 1, really, right? So infinity minus 1 is still infinity. So both are arbitrarily large, so we can say that our limit is heading towards infinity in this case. Letter B, we kind of have to break this one apart because there are 2 functions going on. So let's let that big exponent of 3 over 2 minus x be equal to some other variable, let's say t. And as x is approaching the right side of 2, when I plug in like a value of 3, I'm getting a negative value, right? On the left side, I'm getting a positive one. So I'm really heading towards negative infinity in this case. And so because of that, then I can say that t is approaching negative infinity. And then I can insert t in for 3 over 2 minus x and say now, instead of approaching the right side of 2, I'm approaching negative infinity. And because e to the negative infinity is really super small, it's basically 0. So we can say that we're approaching 0 for the limit there. Letter C is kind of like the previous examples where I'm going to divide. But now here, notice something different. Now I have a square root and I have an x squared in there, but the stuff outside the square root is not squared. So technically, 1 over x is actually the same thing as the square root of 1 divided by x squared. And so that's why I'm multiplying that by the inside rather than the 1 over x. I'm still doing the same thing, or the same value, it's just I can rewrite it to fit my needs. And so in this case, I'm able to get the limit as negative square root of 3 over 2. Okay, have fun.